Welcome to Let Us Learn YouTube channel. Today the session is in Module 4 DC Motors Part 6 about Back EMF, significance of Back EMF, current and voltage relation of a DC motor. So here the Back EMF and then significance of Back EMF is very important question. Often they asked in VTU exam. And then if you are having good knowledge in current and voltage relation of a DC motor, you can easily solve the problems in DC motor. Come on, let us go to the session. In this, we are going to discuss about the back EMF. What is back EMF? This they asked in VTU exam question. So it is very important question. So I mentioned I marked this as a star. So what is back EMF? See, I'm just taken an example, a separately excited DC motor. In this armature winding and then field winding, both are separated each other, and then here this direction it shows the applied voltage, and this direction, that is EB, it shows the back EMF. V is the applied voltage and then EB is the back EMF. See, the EMF always oppose the supply voltage is called back EMF, and it is denoted as EB. Here if I am giving supply, the EMF, that is a voltage which flows towards the armature, and then armature it starts to rotate. Whenever it starts to rotate, it will have some opposed EMF. That opposed EMF is called as a back EMF. So EB is equal to 5ZNP divided by 60A. Due to the motoring action means whenever we are giving the electrical as an input and then output is the mechanical energy. So due to the motoring action, the armature of the DC motor starts to rotate. This armature it starts to rotate. At the time the back EMF is also get induced. Back EMF and then speed both are directly proportional to each other. Whenever the motor is at rest, that is speed is 0, the EMF is also 0. When the speed get increased, the EMF is also get increased. Next, the moving armature conductors cut the main flux, and hence EMF induced in the conductors. According to Lenz's law, the EMF oppose the DC supply. So here the EMF will oppose the DC supply according to Lenz's law. Now here the EMF oppose the supply voltage is otherwise called as the counter EMF. The back EMF is otherwise called as the counter EMF. Now we are going to discuss about the significance of back EMF. Now the significance of back EMF. This is also very important question. Often they used to ask in VTU for 4 marks or 6 marks. So these are the points to be keep in your mind. So due to the presence of back EMF, the DC motor becomes a regulated machine. That is, the motor adjusts itself to draw the armature current. See, due to the back EMF, the motor it becomes a regulating machine, and then it draws the armature current. So the basic principle of this fact is that the back EMF is proportional to the speed. What is back EMF is proportional to speed? It means whenever the speed get increased, the back EMF is also get increased. Whenever the speed is decreased, the back EMF is also get decreased. So at initial stage, the back EMF and then speed it becomes 0. When load is suddenly put onto the motor, it means when we are applying some electrical load or mechanical load, says like brake drum or etc. If you apply some load to the motor tries to slow down. The speed of the motor get reduced. So the speed of the motor reduced, due to which the back EMF is also decreased. Whenever the speed of the motor get reduced, and then back EMF is also get reduced. See here, back EMF is directly proportional to the speed. So whenever the speed get reduced, the back EMF is also get decreased. So the net voltage across the armature, that is V, that is applied voltage minus back EMF, increases, and then motor draws more armature current. So at the case the motor it draws the more armature current. it takes more armature current. Example, if I am using more appliance, the current consumed by the consumer is more. So like that, here if the load is applied to the motor speed it gets slowed down. Whenever the motor speed gets slowed down, the back EMF is also get decreased. So at the time the motor draws more armature current, it takes more armature current. Due to increased armature current, the force experienced by the conductor and hence the torque on the armature get increase. Next, when the load on the motor decreases, the speed of the motor tries to increase and hence the back EMF is also get increase. So the back EMF regulates the flow of armature current and it automatically alter the armature current to meet the load requirement. This is the practical significance of back EMF. See here, when the load decreases, the motor tries to increase, the speed of the motor get increase, hence the back EMF is also get increase. See here, as already we discussed, the speed and back EMFs are directly proportional to each other. Speed increases, the back EMF is also get increased. Speed decreases, the back EMFs get decreased. So when suddenly we are applying some load, the speed get reduced and then back EMF is also get reduced. When the load is decreased, when the load is released, the speed of the motor also get increased and then back EMF is also get increased. So practically the back EMF regulates the flow of armature current. The back EMF is the vital role. It will make the armature current how much it should flow. So the back EMF regulates the flow of armature current and it automatically alters the armature current to meet the load requirement. What is the load requirement? For that, how much current is required? So that is the practical significance of the back EMF. At start, the speed N of the motor is 0, hence the back EMF is 0. See here, at starting, the speed of the motor is 0 because initially the motor will be at rest. When we are giving supply, at the time the motor starts to rotate. Whenever it is rotating, the back EMF is also starts to increase. So motor is 0, the back EMF is also 0. Motor starts to pick up the speed, the back EMF is also started to increase. So this question, that is significance of back EMF, in VTU question they asked many times. So this question also very important. So I mark the star. Next we will discuss the current and voltage relation of different motors. So first we are going to discuss about the DC series motor. The DC series motor is otherwise called as a variable speed motor. The speed get vary. So this is the circuit diagram of your DC series motor. The series winding and then that is a field winding and then armature winding are connected in series. Where IL is the line current, ISC is the series current, IA is the armature current and RSC is the winding resistance of a series field winding, RA is the armature resistance, V is the applied voltage. So in DC series motor, the entire armature current is IA, that is equal to the series field current. Series field current means ISC and also equal to the line current. Line current means IL. So the flux produced is proportional to the armature current. So here the flux which is going to produce, that is proportional to the armature current. So I, that is phi, is directly proportional to IA, that is a flux is directly proportional to the armature current. So now the current relation IL, that is IL is equal to ISC, that is equal to IA, because line current, the series field winding current and then armature current both are connected, all are connected in series, that is series field winding, armature winding and the line current both are connected in series. Now the voltage relation V is equal to EB, that is a back EMF, plus IARA. IARA means voltage across the armature, plus ISC RSC, voltage across the series field winding. So V is equal to EB plus IARA plus ISC RSC. Since already we discussed that IA is equal to ISC, that is equal to IL. So instead of ISC, if I replace IA, so V is equal to EB plus IA, if I take common, RA plus RSE. So flux is directly proportional to the series field current and then armature current. If I substitute here, flux will be directly proportional to IA square. So the DC series motor, the initial torque of the DC series motor will be very high. So always the DC series motor should be run with the loaded condition. Without loaded condition, if you run the DC motor, the speed of the motor will be behind the rated RPM. So always the DC series motor should run in a loaded condition. So phi is directly proportional to IA square. So it is called as a variable speed motor. Next we are going to discuss about the DC shunt motor. The other name of DC shunt motor is called as a constant speed motor or constant flux motor. Here we are going to discuss about the DC shunt motor. It is otherwise called as a constant speed motor or constant flux motor. So this, it shows the circuit diagram of a DC shunt motor. See here the field winding and then armature winding and then supply voltage. All three are connected in parallel. So the voltage will remain constant. But IL is the line current. While it is coming to this junction, it is dividing as IA and then ISH. IA is the armature current. ISH is the shunt field current. So here RA is the armature resistance, ISH is the shunt field resistance, and then V is the applied voltage, and then EB is the back EMF. Already we discussed, always the back EMF which opposes the applied voltage. So it is opposite direction to the applied voltage, and V is the supply voltage. Here this is called as the armature winding, this part is called as the shunt field winding. So voltage across the armature and then field winding is same, equal to the supply voltage. Since these three are connected in parallel, so all the voltage will remain constant. So the current relation IL is equal to IA plus ISH. Already we studied this concept in Kirchhoff's current law. IL is the incoming current, IA and then ISH is the outgoing current. So IL is equal to IA plus ISH. Now for ISH means we are going to find only the current in the shunt field winding. I is equal to V by R, as already discussed in the Ohm's law. So ISH is equal to V, that is the supply voltage, divided by RSH. So we will get the ISH. Now voltage relation, V is equal to EB plus IARA. EB plus IARA, that is the voltage across the armature winding. Or else V is equal to EB plus ISH RSH, that is the voltage across the shunt field winding. Next we are going to discuss about the short shunt and then long shunt compound motor. Short shunt compound motor. In this it shows the circuit diagram of the short shunt compound motor. The shunt field winding, it should connect across only the armature winding. This, it shows the short shunt compound motor. So here the current relation IL is the line current, that is equal to ISE. ISE is the series field current, and then IL is equal to ISC, that is equal to IA. IA is the armature current, ISH is the shunt field current. So here IL, it is a line current, is equal to ISC, that is equal to IA and then ISH, because while coming to this junction it is dividing into two current, but here ISC and then IL are connected in series. So IL is equal to ISC. So IL is equal to ISC, that is equal to IA plus ISH. And then ISH, if you want to find the current separately for the shunt field winding, ISH is equal to total voltage V minus IL or ISE into RSE, that is the voltage across the series field winding. Since IL is equal to ISE, I can make this as ISE or IL. So ISH is equal to V minus IL into RSH divided by into IL into RSE divided by RSH. IL or ISE into RSE means that is the voltage across the series field winding divided by the armature resistance, that is divided by the shunt field resistance. Again I am coming this, ISH is equal to V minus IL into RSE. IL and then RSE are equal. That means this series field winding voltage divided by resistance in the shunt field winding. So V total voltage minus voltage in the series field winding divided by shunt field resistance. That means I is equal to V by R. Now the voltage relation, V is equal to EB, that is EB means that is a back EMF in the armature, plus IA RA, this is the voltage in the armature, plus ISC RSE. Since here these two are connected in shunt, that is parallel, so here they are taken as a IA RA plus ISC RSE. We are going to discuss about the long shunt compound motor. In long shunt compound motor, the shunt field winding on the armature and then series field winding both are connected in series. For this, the shunt field winding, it should be connected in parallel as shown in the diagram. IL is the line current, ISC is the series field winding current, IA is the armature current, ISH is the shunt field winding. So here the current relation is IL is equal to ISC plus RSH. ISC is the series field current, ISH is the shunt field current. IA is the armature current, that is equal to the ISC. Since armature current and then series field winding resistance are connected in series, so the same current will be there. So IL is equal to IA plus ISH. While coming to this junction, it is dividing into two current, IA plus ISH. So IL is equal to IA plus ISH. So ISH is equal to V by RSH, because I is equal to V by R. So ISH means the current in the shunt field winding, that is equal to total voltage divided by the RSH. Now the voltage relation, V is equal to EB plus IA RA plus ISC RSE. Here instead of ISC I can replace IA. So if I take IA as a common, V is equal to EB plus IA whole bracket. This video is very useful for you. Thank you. Subscribe, support and share this video. Let us learn.